Now that we have discussed the steps involved in setting up a heat transfer problem, and we will take one topic at a time and go into detail into discussing the modeling approach associated with that particular topic. So the first is basically the business approximation. So the business approximation is used to define density as a function of temperature, and in this case the density is treated constant in all equations except in the buoyancy term in the momentum equation. So only in the momentum equation, when buoyancy term appears, the density is taken as a function of temperature. In the rest of the terms where temperature density occurs, it is taken as constant. And in this case, the buoyancy force is calculated by using this particular correlation of the buoyancy force, and it is appropriate for small density changes. It should be strictly avoided in cases where large temperature difference is present, and for this we need to specify basically the operating density also here in the operating conditions panel. And this particular approximation is not applicable for species calculation, combustion, and reacting flows. How do we set the operating conditions for the business assumptions? Our business approach is basically go to models, energy, edit, and turn on the energy equation. After that we go to cell zones, conditions, and operating conditions. In that case, after that the operating condition panel opens up and we set the operating density here. We also need to set gravity, which is given here. The gravitational acceleration in 3 components of that is set here. For incompressible ideal gas law, we have to set the appropriate value of operating pressure also, which also comes here. This is applicable for incompressible ideal gas law, which is set here. In case of business model, this is not used. We have to enable the operating density option in the operating conditions dialog box and enter a value for operating density. So for ideal gas law, incompressible ideal gas law, we have to use the operating pressure. For for business assumption, we have to set the operating density and operating temperature. Fluid density can also be defined as a function of temperature in much more complex analysis. For that also we have to go to models, energy, and edit, and after that operating condition panels. And the use this particular slides is basically used to state where we need to use the business model must be used in case of steady state solver, whereas in unsteady solver the business or the ideal gas law can be used. Now that we have discussed business assumption in detail, let us go into setting up boundary condition. What are the different boundary conditions that are available, how to set them up, what is the detailed inputs that are required. So thermal boundary conditions are a very important part of setting up any type of heat transfer modeling problem. As shown here, if we consider a square block also, there may be different boundary conditions at its boundaries that are available, different physical inputs like constant temperature, insulated, it may be open to air, it may be having some flux that is generated at that surface. So depending upon what the real situation exists, we can have different boundary conditions. Let's say we have flow inlets, at that we have to specify the fluid temperature that is coming in. If we have flow exits, we have to specify fluid temperature extrapolated from, if we have flow exits, in that case the software itself extrapolates a fluid temperature from the upstream value. If we have pressure outlets, we need to specify backflow temperature also in case there is a reverse flow. If we have fluids and cell zones, solid cell zones, we can specify energy source, that is thermal energy source. For all types of walls, we can have heat flux boundary condition, temperature boundary condition, convective heat transfer boundary condition. We can also have external radiation and combined external radiation and external convective heat transfer. We will discuss these one by one and how to set them up within Fluent. So let's say we have a heat flux boundary condition, that is we have to specify what is the flux that is available at that particular surface or boundary. This is used for a fixed heat flux condition, and we set the appropriate value for the heat flux at the wall surface. So we have to select the wall surface boundary condition. So this is the way we have to select at the wall surface. Its panel opens up. We have to go to thermal boundary condition panel, and we have to click on heat flux and activate the heat flux option, and we have to give the heat flux value here in the heat flux dialog box. Zero heat flux means adiabatic wall. So if we have to model insulated, we have to basically say 0 here. So this is the heat flux that we are specifying in this particular option, and using that, basically the and also using the wall temperature and heat transfer coefficient T free is calculated, and this is how the process continues. So this is how it is used internally, that is the heat flux boundary condition.